Okay, Gusto is in. That's good. So today is not the prayer day. It's gonna be Friday. Start at 1 o'clock. You will come back around 1:30, right? Don't you think starting from 12:30, right? 12:30 for one hour is not enough for prayer? No? So as I see you, sometimes you don't come back. So you have to stay out there for prayer meeting until 2? Jeez, so you're completely out then. Okay, so you've got to catch up using the videotapes. Ask Mr. Num, or you can access our internet, so then you should spend an hour to catch up that. Okay, we barely started the probability density function, or simply joint the probability function, 2 parameters. So here I use x and y. You can use any 2 the random variable. So this is no longer expressed in 2D plane, but 3D, the volume. So density function is like a upside down cone shape. If you visual as I talk Monday, think about the upside down, the bell shape. It's really bell. That's a volume. Okay, and this is a capital the P, so this is a probability distribution function. So sometimes people use, sometimes I use P subscript XY, okay, then XY parameters, which is defined as probability such that 2 random variable. So K is event, like a time t1. If it's a discrete probability you're talking about, then that's really x1 and x2, y1, y2, the vice versa. So x is less than or equal to x is upper limit. It's not or, it's and. Y is less than or equal to the y, which is really threshold. X and y here is a threshold, the limit. Okay? So it's a definitions. So the range, x has to be less than, this is at any event, I'm telling you. So x is less than equal to infinity, and y is less than and or, this is, you can use or, equal to infinity for all event. Case event, okay? So probability distribution function minus infinity, x is minus infinity, and the y is just any event to y, any random variable y is equal to 0, or you can set y as a minus infinity, x is any random variable, any place. But can you see it? You have to see it. Why this case is 0? Why this case equal to 0. Sometimes doesn't visualize well. The y can be any position. Think about the probability density function or probability distribution function. And x could be negative infinity, y could be negative infinity. It's obvious if I write this. If I write this, it's gonna be very obvious. I'm gonna say this is xy. This is a probability density function xy. So I'm looking this way, and so I'm gonna just put this guy contour. Look at this. I'm gonna set the x is a negative infinity. This is a negative x. It just goes just across a section in x and p plane like this. Think about extending all the way this guy very close to 0, almost to 0, but does not touch, curve doesn't touch the x-axis. So think about you have a cut in the xp plane, which means this area, this portion is almost 0. And regardless of the curve in the y direction, it can be any. As this x or y approaches to infinity, negative infinity, then area, eventually volume, is 0, because this is just almost touching the xy plane. You see that? So if you take the area, take the volume, it's 0. Can you see it? You have to see it. Otherwise, this doesn't make sense. This is equal to 0, and this is equal to 0. Once again, I'm telling you, this is approaching all the way through here. Okay? Then, if I just draw the y-axis along here, this is almost a touching curve, touching the x, in this case x-axis here, and the y-axis is almost the curve, or the volume is almost flat. So if you take the volume for the volume, which is almost close to xy plane, is approaching to area, the volume approach to 0. That's why this or this is equal to 0. However, if x and y goes to the infinity, then it keep adding the volume, then as it goes to infinity, the whole volume of the probability distribution function will be the 1. So if you just going into the 2D, This is 0. It looks like it's shifted. But, this is x. This is one random variable. So this goes to the negative infinity. Then as it approaches to negative direction, this is minus infinity. So if you want to add all the area here, then this threshold goes to negative, area is 0. But if you keep adding up the area as x approaches to infinity, it contains the whole area. Make sense? So if this threshold approaches to plus infinity, what's the total area? Total area approaches to 1, right? As I look at your eyes and, geez, I can't believe that. 2D is easy. But 3D, when you get into the volume, is a little bit more thinking and visualization as it approaches to either axis, x or y. As it goes to minus infinity, then total volume is just disappears. Okay? And as x and y move to the positive direction, it keeps adding because it's all including the volume already exists here, but as it just goes to one, approach to positive x or y, then whole volume will be the 1. So that's what this is. So definition. This is not the PowerPoint. This is PDF file. Okay, so next is a probability density function. Probability density function, as we did for the random variable x, we did, but now the joint or two random variable, the probability density function, is this probability such that x is between x and x plus delta x, y is between y and y plus delta y, then divide by not just the delta x times delta y. So clear definitions. And the probability density function is always positive or 0. The whole volume under the probability density curve is 1. But here is mistake. Where is the mistake? There is no z. This is the delta x and the delta, the y. Okay, that's what it should be. I want to make sure. Okay, so probability distribution function capital P is integration for the x variable minus infinity to the first x, and next is minus infinity to the y. So it's two variable, two integration parameters. And then the relation between probability density function and the probability distribution function is something like a slope in xy graph, okay? So y could be like a probability distribution, and delta, and small p is a probability density function. So it's the differentiation twice, one by x and the other by y. So it's like between the displacement and velocity relations, okay? So two variables, so you have to first differentiate with respect to x, then y, okay? Then you will get the probability density function. So it's a joint probability. You have to visualize the volume rather than area. Two random variables. So it's a definitions, okay? Okay. So here, what I did was, well, let's read this one a little bit. The probability density function x and y individually are obtained from the joint probability density function. In other words, now this is a joint probability, okay? Then I'm going to condense all the y directional volume, then condensed right into the probability function for the y. Then you have to integrate out these directions. So that's what it happened here. So to get the probability density function of x, then you have to integrate out by the y. And for the y, you have to integrate out by the x. Okay? So sometimes that's useful. So this is kind of, this curve is, let's say, the this case is not condensed out any directions, but it's a 3D, simply 3D, the volume view. And another, the occasions you are always facing is x and y. Sometimes that could be statistically independent. In other words, y does not caused by x. It is really too individual. Not after marriage. Before marriage, two perfect individual whose thought process is completely different from one another. Okay, that's independent. When you say dependent, it's correlated each other. So good analogy is like married situations. So for the married situation, one person's thought is almost dependent to other person's thought. After you marry, like over 40 years, when I look at her, I give some thought. She knows 100% what I'm thinking. That's a total dependent. So that's what we're going to talk in chapter 3, correlation. So in this case, independent, statistically independent means pxy, joint probability function, can be expressed as a multiplication of the the px and the py. Because there is no correlation term. Correlation term is 0. So it's purely px and py, just multiplying together, and that's the situation. So here, when these random variables are the statistically independent, pxy joint can be simply the multiplication of individual, the probability function. But now I'm going through all the definition, and sometimes, always like a couple of weeks after assigning one homework to another, then you have a chance to practice a little bit on that. So this is a density function, this is a distribution function, same thing. It's purely multiplication when two variables are statistically independent each other. One does not cause to the other. Y is not dependent on X. Okay? Okay, keep visualize for the single random the variable situation. So let's say expected value of x multiplied by y by definition is equal to probability density function, which is a joint probability density function of small pxy multiplied by, in this case is simply x multiplied y, then this has to be simply xy. If this is a function of xy, then this should be the function of xy. So definition, right? For the joint probability, the situation is the same, which this is expected value. Okay, this is the integration is minus infinity to infinity for x and y both. Oh, so it's another case. The case is like here in this case is just a function xy. This case is you are talking this is function of x and y. If this is the one you are looking for the mean value, then this multiply that, then you have to integrate in x and y domain. Okay? So look at this. Look at this. If x and y are independent variable, okay, then I can say that exactly like this, okay. But x and y are independent, then I can split the pxy as a px multiply py, right? Yeah. So I multiply simply 2 here. This is this could be just a step before. This could be xy times pxy xy, but I can split 2 terms, one in x domain, the other one in y domain. Is 2 independent terms I can generate. So this is x, this is y, God bless you, and this is really when you say expected value, which is mean value, then I can simply say E, the mean value, expected value of x multiplied by expected value of y, which is only good for the case two random variables are independent, playing each other, no correlations. So some example. So I do one here, you do one at home. I don't think I assigned in the homework, but you should do it. When I say do it, try it. Don't regret in the exam. Oh, that was classroom homework. I forgot to practice. I want you to practice. So here, consider two sine wave of constant amplitude with unknown means random phase angle, the phi, okay? So I can write the two functions here, simply sine function, okay? Phase angle is random, I said. Constant. So x is equal to x naught sine omega t. Another one is y. Yt is equal to identical with the phi, the angle, shifted angle. I said the phi is a random variable. Then my question is, what is the expected value of xy? And another question is, what would be the expected value of xy squared? Okay. I could say, what would be the expected value of x plus y? So first, the example problem, I'll do. The second example problem, you do. So I'll do this and you do that after you return to your office. So let both time histories be sampled at any arbitrary time. So don't ever think, oh, phi, I can make a random variable. T naught, we never had assigned t as a random variable. Why not? Omega you could set as a random variable. But here, usual situation, angle phi is a good selection to set as a random variable. But here in class, why not set t naught is set as random the variables? Of course, here is a phi random variable. The t naught, I set as random the variable. Then first, what you have to do to get the expected value, you have to get the probability density function of the random variable, which is what? T naught and phi, right? So first is a t, next is a phi naught, but this x is simply x sine omega t, but the y is x sine omega t plus phi. So first t naught. What's the range of t naught? It's omega. So 2 pi over omega is, the unit is the time, right? Because this is angle divided by radian per second is a second. And usual, the assumption, this is assumption, is a uniform probability assumption. Chances to occur is all even at any time. So it's a straight. So area has to be 1. So the amplitude in the probability density function of T naught, you have to, area has to be 1. 1 has to be equal to 2 pi over omega multiply question mark, which is inverse of this guy, omega over 2 pi. Right? So its period is going to be from 0 to 2 pi over omega in this duration. And for the phi or phi, angle is 2 pi max. So the uniform probability density function, it has to be the inverse, which is 1 over 2 pi. So this is what. And now look at this. This is a so all I'm doing is trying to get the E value, right? E, expected value. Expected value of x, y. Then I have to have x, y, then probability x, y, dx by the definition. That's what I'm heading for. Then every entry you have to really get the information, then you can solve the problem. Probability such that T is between T naught plus dt naught is equal to the, it's really, so this is T naught, this could be T naught plus dt naught, which is simply the probability density function right here is a straight step function, uniform probability function. So simply P T naught times dt naught is area. So that's a straight multiplication. And PT naught, this portion is right here. So this guy, this is omega over 2 pi multiply dt naught is that. Similar situation for this probability such that phi is between phi naught plus d phi naught, which is that area, which is simply that guy multiply d phi naught. Amplitude here is 1 over 2 pi times d phi naught. So I want to do the similar situation for the case of xy square. Then you have to get the pretty close but more calculations. Then now for the joint, for the t and the phi, then you have to get the volume. So then you have to have this guy and that guy multiply that guy. You have to multiply this guy. You have to multiply it. And this, the rest, is a joint probability density function. That's what you have to look for it. And that's what you have to get the expression. Okay. So so this is almost done to get the joint probability density function. is in the previous page. This is exactly that. It has a range for T naught, and the phi naught has to have, starting from 0 to this, from 0 to 2 pi. So now you're about to ready to compute the expected value of x multiplied by y here, then which is xy times the joint probability density function integration from minus infinity to the infinity. But infinity, below 0 doesn't mean anything. Lower limit is 0. You can start integration, lower integration limit as 0, 0, 2 pi over omega, and 2 pi. So it's very clear. So which is x naught square sine omega t naught, and another one sine omega t naught plus phi, and the probability density function. If you do the integration, it's easy to look, but you have to do the calculation, okay? So sometimes some work to do. So if you do the double integration, it has to be equal to 0, which means the expected value of a function x multiplied by y happen to be the 0. Then question is, what about the expected value of xy square? So the answer is x to the 4th power over 4. Would you do that? So don't spend more than an hour. It's not worth it. So this is xy square situations. And there are a lot of, I can make a few different similar problem. I can say, what about the mean square value? What about the standard deviation? I can assign the omega as a random variable for the practice. But if you do two of them, approach is really same for any situation. What about the variance? So please do the practice. Okay. Now, lastly, for the joint probability function, this conditional probability, I just show you just a couple page for simplicity. It can be like a 10-20 page talk within 20 page like a volume for conditional the probability, but I want to introduce the clear definitions and understanding of joint probability function. And px and straight bar sometimes use slash. It's really same thing. It's no difference. And the probability density function can be straight down the y over y. Doesn't make any difference. Conditional probability is really means probability of x given the y. You can read it that way. Given y. So listen carefully. This is a conditional probability density function of x given y. Conditional probability function for x given the y. So here using this joint probability density plot, this is the volume, this is a slice cut right in the py plane. This is a py plane, p, and this axis is y. And for this one, as you see here, slice was in x p plane, so you can see that kind of the volume. So for the pxy dx is elementary volume over the given volume in y-axis. So elementary volume means in this joint the probability density function, that volume, which is dx, which is dy, and you can draw the differential, the volume. Can you see this? Yun-gyu, you can see that. That's elementary volume within the dx, dy, and the pxy. So this is height, and this is d. What's this? This is which axis is not clear. This is x-axis, and this guy is a y-axis. This width is dy, and this guy is a dx. So elementary volume is what that means. Differential the volume over the given volume of y. So this is given the volume of the y, is it said the shaded volume, the volume of the shaded strip. So which means given means this is a given shaded. Denominator has nothing to do with the whole joint, the probability density volume. It's only slice. The picture is quite different. For the conditional, the probability function. So as you look at this, so denominator is integration. By the way, this is dx. I think I made maybe already correction. Joint probability times the dx. The width here, this is a point is a y, and this is dy. So if you take the integration of the x, which is really this, times dx, just a minute, dx, just a minute. Let's look at, you have to be kind of very careful. First, elementary volume is concerned the height and the dx and dy, very clear. And below is dy is width. It should be width. Width is a constant, right? dy. Right? Width is this. Width. That's a dy. Huh? And this integration with respect to dx is area of this guy. Right? So which means denominator, this guy is the volume of this strip. Given. So then if you look at dx, dy, Oh, this is integration parameter right here. So dy, you can cancel, right? And the pxy dx and the py. So this reduced down to the conditional probability density function of x given y is equal to pxy, joint probability density function, divided by pxy, probability density function of the y. So a little bit more. And after you understand once, that's all you need to know. If x is a random variable independent of the y, then px/y is simply px, because it's nothing to do with the y. Play individually. So that's, you can say that, right? Then pxy is px multiplied by the py. But if it's a conditional probability, then pxy, joint probability density function, is px/y times py. So it's a little bit there. I'll look for some nice some example problems. But this is what last definitions. And we have done the first order, the Gaussian density function and distribution function, and the joint probability density function for Gaussian, which means sometimes I mentioned to you, use the name as a normal. Sometimes Gaussian is identical things, and for the normal or the Gaussian joint distribution function, the density function is, what's a px, py? Standard deviation of x and y, so its mean value is there. Then now another term is here which relate the x and y. So rho xy is called the correlation coefficient, which is coming in chapter 3. And rho xy depend on the degree of correlation. Rho xy's range is from -1 to 1. So rho xy falls between -1 and 1. And no correlation, all single. Your case, rho xy is equal to 0. No, it's all single here. Oh no, I'm sorry, Chabom is not single. So he has some value on rho xy. All others are absolutely 0, which means no terms, no last term. Rho xy, this is, I said, called the correlation coefficient. Some people call this as a normalized covariance. I think no more R or L? L? Okay. Normalized covariance. Or correlation coefficient. Okay. So we'll talk quite a bit on this. And if x and y are statistically independent, you drop the last term, and this is simply multiplication of two terms of px multiplied by py, both are Gaussian density function, normal density function. Okay? All right, so now you're the expert in probability functions. And whole semester course is done in about a week and a half. That's it, okay? All right, I'll see you on Wednesday. Any question? What? I'm sorry, Friday I'll see you. Yeah, Friday. And makeup class is after I return from the conference. Then we'll do the 1 hour every Monday for 3 weeks. Okay, good day.